We're now at the point in organic when we get to take a look at the very last type of spectroscopy that we have yet to look at. There are other types, but this is the last one that really kind of yields any super useful information that requires an entire lab to discuss. Honestly, mass spectroscopy is probably it's better known as mass spectrometry, but it's not really that important. Usually, spectroscopy has to do with the interaction of light with matter. In this case, we're actually not worried about the way that light interacts with matter. Basically, what we're going to be doing or what a mass spectrometer does, is it basically takes a molecular compound and bashes the living hell out of it, breaks it off into little pieces. I always, if we were in lab, I would kind of do a silly demonstration. The gist of which is like if you kind of imagine if you have like I don't know, a Swiss watch or some like really fancy piece of machinery. And you want to know kind of like how all the parts are put together. You could just bash the heck out of it with a hammer, and then buy another watch and bash the heck out of that with a hammer, and then buy another watch and bash the heck out of that with a hammer, and kind of compare all the different pieces to kind of figure out how everything is connected together. That's kind of what's happening in a mass spectrometer. The important thing to recognize is the only things that you're going to see in a mass spectrometer are going to be things that have some sort of charge, because you're putting it through a big giant magnet, and anybody that's had some physics recognizes that a moving charge through a magnet kind of creates its own little magnetic field. And so it's just this kind of idea, which is kind of symbolized here, that if you kind of put a detector at the other end of the tube of the mass spectrometer, it turns out that the heaviest particles are going to have I guess the most momentum and will be deflected the least, whereas like the lightest particles, they're going to be deflected a little bit more by the magnet because they have a little less momentum. But we don't care about all that physics crap. What we care about is the way to look at a spectrum and to actually get some information out of it. I will say, by the way, this is just a typical mass spectrum that I just kind of grabbed. And one of the things that you'll see on this spectrum is that it's really hard to get like real quick information. A big part of what I'm just going to kind of review, initially at least, are the rare, like really quick bits of information that we can get out of something. It really is something that you really have to sit down and think about, and I'll show you a couple of kind of typical things to look for given functional groups. Honestly, your ultra secret text has some really good review of the actual fragmentation patterns of this thing. There's some really weird arrows. Many of them are just fishhook arrows, meaning just transfers of like one electron in a super potential energy highly charged state. It's all kinds of crazy stuff. And so most of it I'm going to kind of leave to you to figure out. And I'm going to just kind of summarize the most important things I'd like you to get from this. So one of the very most important things, I guess, that we should talk about is the one thing that is super useful that a mass spec can give you is the molecular weight of the compound, right? And you'll notice here that the kind of the rightmost peak is labeled that 100 right there, and hopefully if I've done my math right, that should correspond to the actual molecular weight of the hexanal that you see listed off in the corner here. And so that's something that's really useful, right? If you don't know what the heck something is, it's really useful to have its molecular weight. And usually that's the peak that is farthest to the right. This MZ is mass over charge. Most of these things have a charge of 1 plus because it loses an electron initially. And that very first electron that is lost, when that big giant fragment goes through the detector, goes through the magnet and then to the detector, it'll actually be shown here. One of the things you'll notice is that there's not too much of that, the fragment that corresponds to the molecular weight of the compound. What happens often, and this is a huge complication in real life, is that you don't actually get to see that that M plus peak. And instead, like this guy is labeled obviously, but if you imagine just having taken this spectrum, you might see this and think, oh, well, is that the molecular weight of my compound? And sometimes it's actually missing. The good news is that's very rare in anything that I'm going to give you, that just about always you'll see that M plus peak. So speaking of M plus, right, that's called a molecular ion peak. So that usually corresponds to the molecular weight of your compound. Now you'll notice that there's a couple of other lines in here, right, that have one atomic unit of mass more, right? Well, I guess here there's actually a +1 and a +2 and a -1. And so one of the things about a mass spectrum is it very, very sensitive, right? There's like a really nice resolution. And so what you're actually looking at there are the various non-abundant isotopic masses, right? So for instance, there's very little C13 in a compound that contains carbon, but there is some, and so that'll actually be something you can resolve on a mass spectrum. So anyway, so if you ever hear me talk about an M plus peak or a molecular ion peak, I'm talking about the molecular weight of the compound here. Given the natural abundance, kind of the typical natural abundances. The base peak is kind of an oddball thing that you only really have to worry about if you're really going to do this more. And that is the tallest peak in the spectrum that everything else is measured according to. So what you'll see, a mass to charge ratio, right? And you'll kind of notice this like fragmentation pattern. One mistake that students make is when they imagine their, Swiss Army Swiss Army watch that they bashed with a hammer, they kind of think like, oh, that must mean that this peak, that fragment became this fragment, which became that fragment, and then became that fragment. Now, it's not quite that linear, right? It could be that this peak right here might have decayed to that. That peak right there could have decayed there. That peak right there might have decayed there. And you'll notice that the relative intensity of these different things is telling you a little bit about the most frequent fragments, right? So there's that relative intensity scale, all measured according to the base peak. So as I said, I was going to highlight the quick information you can get out of just looking at a mass spectrum. Well, one is the molecular weight of the compound, most often. And then the other thing is that it's a really good way to tell that there are halides present. It turns out that due to the natural abundance of C35 and C37, there's almost always, if a Cl contains something, a whole bunch of fragments that have a 3-to-1 ratio. Certainly the molecular ion peak will have a 3-to-1 ratio. And then if it's a bromine, because bromine exists as a 79 and also an 81 in roughly equal quantities, you'll also tend to see 1-to-1 ratios for the molecular ion peaks of these guys. So let's just kind of take a look at a typical alkyl chloride, right? And so there you see that 3-to-1 ratio. The thing is that because this is such a simple compound, one of the first things that happens is that Cl falls off. Right? And so what you should be able to see is, first of all, this really huge 3-to-1 ratio in one of the fragment peaks. I'm not sure if this is actually, oh yeah, see, it actually even says that the peaks of the molecular ion are absent, so that's nice. But this is one of the fragments, right? There's that 3-to-1 ratio. If you had a bigger compound, you'd see a whole bunch of these, right? You'd see a whole bunch of 3-to-1 peaks. That's really typical, real quick information you can get out of a mass spectrum. Typical alkyl bromide, you'll see these kind of 1-to-1 peaks. That really only happens when it's something that contains a bromine. And even more than that, you'll see this relative to this M plus peak right here, a loss of 79 units, right? And so that's indicative of losing one of the isotopes of bromine. So what we're going to do is I'm going to kind of show you where to find some of the fragmentation patterns of different functional groups. As I said, your ultra secret text, the Wade text, has a really great discussion about mass spectrometry. I will say that the introduction of your lab itself that I'll show you in just a second has a pretty decent job, but this one really goes through what's going on in the various decays of these things. It also has a much better discussion of the physics than what I did behind a mass spectrum. So I'm just going to do kind of a quick summary of a little bit of the information in this particular section of the book. I definitely recommend you take a glance at it. They'll actually go through in quite a bit of mathematical detail exactly what's going on in the different fragmentation patterns that are open to different things like alkanes and then different functional groups. So, definitely take a look at that, but I'll just kind of try to summarize some of this stuff pretty quick. So here's a really boring compound, an alkane. One of the things that you really are going to want to learn to do in a mass spec is, first of all, look for the molecular ion peak, and it is almost always an even number, right? That even number, that 226, doesn't really surprise me too much. And then one of the things you'll notice is as you look down the column here is that everything else is odd, right? That is the normal thing that happens in organic chemistry. If it is not an even numbered molecular ion peak that has a whole bunch of odds, let's say that it was an even numbered peak here, but then there was like a fragment, let's say instead of this being 57, that was actually an even number, like 56. That's usually something that is indicative of a special kind of functional group, right? And it makes it really hard to look at, and it's not something that you can get really quick information from, but that's kind of one of the things that I started to develop as I was looking at these things. I would kind of check to make sure that this was even, all these guys were odd, and if it was anything other than that, I knew that it was trying to tell me something. Whether or not I could figure it out was sometimes up to debate. So here's a great example of where it's pretty obvious that something weird is going on, right? I look at this thing, I'm like, okay, I'm looking for my even molecular ion peak, and whoa, it's odd. And even more so, I look through all these different numbers and I'm like, oh my God, they're even. That's a really quick way to tell that you have some sort of amine. Of course, usually you'll have some sort of IR that's coupled with this thing, and so you probably already knew there was an amine there. But just in case, you were looking for quick information there, that's kind of one thing that I look for. And so if you got a whole bunch of mass unit peaks, or sorry, even numbered peaks, and that molecular ion peak is odd, that's almost always indicative of an amine. Obviously, there are like mathematical games you can play where if you have two nitrogens, that kind of goes out the window. And so, this isn't, words to live by, but just kind of like broad brushstrokes that I kind of learned to recognize. So other functional groups kind of developing that theme. So for instance, you're looking for the molecular weight of the compound, which it kindly tells you is missing there. If they label, they being the people that are putting the spectra in here, have labeled something that is like an even number, that's screaming to you. Even more than that, the fact that you lost 18 mass units, if you remember the weight of water, that's actually the loss of a water fragment. And so that's kind of like what we're looking for. We're kind of looking for these fingerprints in terms of interpreting these mass spectra. If you actually wanted to see, where that water peak actually comes from, these are some of the crazy, cleavages that are possible. And again, if you are interested in the actual mechanisms and the whys and the whats, I'd take a look at your book. So that's pretty classic alcohol territory, that loss of 18 mass units. Again, sticking with that analysis where we're looking for an odd numbered molecular ion peak, looking for an even numbered one, and if it's odd, it's telling us something. Well, this one's got a nice even number, but then you look through all these things and you see these odd peaks, but then there's this even peak hanging out here. That's almost always, and by the way, it's a lot more than a loss of 18 mass units. That's almost always due to a loss by McLafferty rearrangement of a mechanism that looks like this, right? And again, we could really get into the weeds here and talk about each individual fragment, but really all I want you to do is to be able to kind of get some quick information out of this thing, and then in just a second we'll take a look at what I'm going to ask you to do for the lab itself. So there's that summary in your book that includes common fragmentation patterns. And then, of course, if you want to know the exact mechanisms, then you can certainly take a look at those. All right, here's your activity itself. A pretty meaty introduction section, a bunch of different fragments for that you can learn to recognize if you really want to. A little bit of how each functional group degrades. As I said, your book is a lot better. So what am I actually going to have you do in here? Well, it turns out the most important section, honestly, are these first three questions, right? And this is going to require you to do some of those degrees of unsaturation calculations that we talked about a little bit last term. It's also going to ask you to kind of use a periodic table to figure out exactly what a formula is. And then what I'd like you to do, just pick out, let's say, 4 of these different examples right here, and just kind of do some work, try to figure out exactly what the molecular formula is, and then suggest a structure that's consistent. What I really don't want you to do is to really dive in. Like, let's say I'm going to answer this one. What I would like you to not do is tell me every single one of these fragments, where every single one of the labeled fragments comes from. What I'd like you to do is I'd figure out, based on your calculation, I'd like you to figure out how many C's, H's this thing has, and then just suggest a structure that is at least consistent, let's say, with the loss of a fragment going from here to here, or maybe here to here. And you can put as much time into this as you want. If you really want to get the exact answer for every one, you're probably going to go bonkers. I really would just choose 4 of them and do your best, and I'll give you a little bit of feedback when you actually submit it. All right, good luck.